presentations are on the LPI YouTube channel. And we want to remind you to join us next month. I believe it's May 12th for the final talk in this series. So before tonight's presentation, though, we want to we have a couple poll questions we'd like you to respond to. So Grace, if you could bring those up, please.
Sure thing. All right, we are live on YouTube. So if anyone is having trouble with Zoom, you can head over to LPI's YouTube page and you can watch the live stream there. Okay, so give me one moment. All right, so we've launched 2 poll questions. If you are joining us from the Zoom app, you should be able to see. If you're on the browser, you might not be able to. But we want to know if you have attended any of our speaker series events before, either in person or virtually. If it's your first time with us, or if you're not sure, that's fine. And then we want to get an idea of how familiar you are with this topic, with the James Webb, with exoplanets, with the search for life beyond our own world. So take a couple of seconds, put in your responses. About 5 more seconds. And 3, 2, 1. Okay, thank you all. We've got a bunch of new people in attendance and a wide range of knowledge. And I have one more poll question. Number 3, here we go. I'm getting a message that my internet's a little unstable, so hopefully you're able to see the poll. We just want to get an idea of who we have here in the audience. So you can click multiple options, but are you an educator, a student, a scientist, and where are you joining us from? Are you local to Houston? Are you in the US, or are you farther away and you're joining us internationally? So again, just take a couple of seconds.
Any feedback on your article?
All right, and I'll stop this in 3, 2, and 1. Okay, thank you all for participating. At the end, we'll have Q&A, we'll have a couple more poll questions, and when you leave, you'll be sent over to a survey. We would love your feedback, so please do fill that out. Okay, I'm all done. Thank you.
All right, thank you, Grace. And thank you all for completing those poll questions. They are very helpful for us in terms of planning our future series, however you say that for plural. Okay, so right now I want to introduce tonight's speaker, Dr. Néstor Espinoza with the Space Telescope Science Institute, which is in Baltimore, Maryland, here in the US. If you've heard of that before, it's probably because you're familiar with the Hubble Space Telescope and also the James Webb Space Telescope. Big astronomy institute out there on the East Coast in Baltimore. Excuse me. Out at the STScI, he is an assistant astronomer. And he spends time studying the universe with with James Webb as soon as it starts doing that, collecting data, as well as the TESS instrument, which is searching for exoplanets. And he does outreach too. I found this very interesting. He records podcasts and does radio shows for a radio station back in Chile, which is pretty cool. So without any further ado, Dr. Espinoza, I'll leave it to you.
All righty. Well, thank you very much. I'm honored to be part of this series and excited because, Webb, this beautiful telescope that we have up and running, that today we share with the world, that it's in focus, it's aligned, all the the mirrors, it's everything ready, and we're just jumping into instrument commissioning. We're just gonna now, in a little bit, try to do to check the science instruments of Webb. So this is like a very exciting time to be talking about this beautiful telescope. And again, I'm honored to be able to be sharing this this talk with you folks. I started sharing my screen, and I hope you can see my slides.
Looks great.
Awesome, great. And the title of this presentation is, it says here, Investigating the Origins of Life with the James Webb Space Telescope. Again, it's an honor to be able to talk about this today and tell you a little bit about how Webb is going to follow the fingerprints of life, like what we understand at least as life. So this story that I'm going to tell you tonight has three main protagonists. Of course, the first protagonist is the telescope, right? This beautiful telescope. If you're not aware of what the James Webb Space Telescope is, it's a telescope that we launched back in December 25th. We've been joking with some colleagues that it's one of these mornings. It was a Christmas morning, and we were as excited as the little kids that were about to open the presents. So this was like the best present ever to see the launch. And it's a 6.5 meter telescope that it's very, very far away from the Earth. It's 1.5 million kilometers, something like 4 times the distance between the Earth and the Moon. And we sent it there because we wanted to be as far as possible from us that we irradiate some light. So we wanted to be, quiet and alone. It's functioning perfectly. We're undergoing commissioning of the telescope right now, so it's very timely to talk about the science that this is going to do. So this telescope is, one of the protagonists of the story that I want to tell you. The other protagonist of this story that I want to tell you tonight, it's the other worlds. So there's other worlds around other stars. I'm gonna tell you a little bit about that in a minute. But those other worlds are, of course, the other protagonists of this night. And of course, there's other set of protagonists, which is us, we at Earth. We are also protagonists of this story because we are exploring, we are, bringing this window into space with this huge telescope in order to explore the cosmos and explore the fingerprints of life out there. Now, to motivate this whole story, I really want us to start here at home, right? This is Earth. You all know it. This little pale blue dot, as Carl Sagan would put it some years ago. And this planet is basically, if you think of everything that has happened, everything, every life form that we know of, the whole story of life forms on Earth, all of those have happened here, right? In this little pale blue dot that looks big, but when you put it in perspective, when you look at it from afar, it looks very, very small. This is a picture from the Cassini mission. Cassini mission took a selfie for us. What you're seeing, this little dot dotted with this little arrow that says here, that's us. That's home. So taking in a little bit. So from Saturn, we are a small dot, like the small dots that you look at the night sky. And further, we're only one dot in this 8 or 9, depending if you like Pluto being a planet or not. Pluto is still a planet in my heart. But we're only one dot in this set of planets in our solar system that orbit the sun. And our sun, it's only one star from the hundreds of thousands, millions of stars in our galaxy. Of course, we cannot take a selfie of our galaxy because we haven't been able to get out of it. But this is our best model, say, of how the galaxy looks like. And as you can see, this immensity of stars that you can not even count them here. We're just one little dot. Our sun is just one little dot in this image. And furthermore, our galaxy, the Milky Way we call it, it's only one of the hundreds of thousands of millions of galaxies out there. So we're really, really, really small. And this, this makes you think. So I just want to repeat the numbers, and I'm putting them in like the actual numbers here. So the estimation is 100,000 million galaxies, and each of them has in the order of 100,000 million of stars. So think for a moment on the possibilities, right? Think on how many worlds are out there. What are the chances that we are alone, or what are the chances that there's other companions around there? Just to give you an idea on the statistics that we know of other worlds, we know today, with all the studies that we've been making, that on average, there's at least one planet around each star in the night sky. This means that when you go out at night and look at a random star in the sky, chances are that the star that you're looking at, it's not alone, has planets orbiting around that. So this makes you think again, like, what is our place here? Do we have a place? Are we incommunicated, or are we alone from other species? And this has been, for long, and still today, the very big question for which I'm completely agnostic, and I'm 50-50 chance on what might be the case. So there's this question on how special are we? How special is our solar system, but also how special is life on Earth? And again, there's two options. So first one is we're special. So maybe we were lucky, and this is like the planet with life in the Milky Way, and even maybe in other galaxies as well. But there's this second option, which science fiction has made us aware of, which we're not, that maybe we're just one more system in this fluid tsunami of worlds out there that have other forms of life as well. The truth is that today we don't have data to actually answer this question. Today, it's a 50-50 chance. Could be both. Could be, it can be one or the other. There's not many data points, but this started our exploration. This question is at the bottom of why we do this kind of exploration of other worlds. And speaking of other worlds, so we've advanced a lot on this topic. So as of today, and if there's one number that I want you to go out from this talk, is this one. As of today, we know over 5,000 worlds orbiting other stars. And we call them exoplanets, and that's short for extrasolar planets, so planets outside the solar system. And we've gathered into teams. There's people that follow stars and try to discover new planets. It's an exciting topic. I work on this a lot, like discovering new worlds. And we've made a ton of advances. We've discovered a crazy amount of worlds, and the properties that these worlds have. They're also they beat any science fiction story. In terms of where they are, so here's a model of our galaxy. And the planets that we've discovered are in certain sections. I'm going to put them here. This is a beautiful plot made by Vivienne Parmentier from the UK. And each point that you see here is one exoplanet that we've discovered. And the different colors, they know different techniques. I'm not going to go through all those techniques. But I do want you to know that these points it doesn't mean that these are the only sections in which there's exoplanets. Actually, if we had infinite wisdom and infinite technology, I'm pretty sure planets will be scattered all around. You will see this picture full of points all around. We don't see that because the methods and the techniques that we use, they mostly focus on discovering planets around nearby stars. And here's, on the top left, there's a close-up, and you can see that most of the worlds that we know of, they're discovered around our sun. There's certain regions as well in which we've uncovered, we have gone deeper with certain telescopes. But it's of course it's a bias, really. But I wanted to show this because we've only scratched the surface of where these worlds might be and what this world might look like. We only sample a tiny bit of the galaxy. And we're about to jump in the next few years into uncovering planets all around the galaxy, which is extremely exciting and, of course, a topic for another talk. But now now that I have given you a little brush of what we have done in discovering exoplanets, now comes the next question, which is, okay, you have these worlds, but how do you follow life's fingerprints in these worlds? And this is a tough question because, of course, the concept of life is based on what we understand as life here on Earth. So it's very biased, most likely. If there's life out there, it might be completely different to what we're imagining or to what we experience here on Earth. But then again, I always like to compare this example as, you imagine that if you're getting to your house and somehow, it's dark at night and, all lights go off and you don't find your keys. But, there's that tiny little piece of light, like a light bulb that it's on, by chance. And that's where you start looking at. You won't start looking in the dark directly. The first place that you look, if everything, turns off, there's on one little light bulb that it's on, it's where you see light. So it's the information that you know. And that's why we focus on search for life, basically, and following life's fingerprints based on what we've experienced on Earth, because it's what we know and what we experienced. By the way, we don't even know every detail on how life forms here on Earth. There's people that study that for like a career, for a lifetime. But we're gonna follow some steps on this. And as far as we know, the cosmic recipe for life, like if you're a chef of life, say, involves 3 big steps in terms of astronomical phenomena. The first one is that you need to make a star. And making stars and seeing how stars are born, it's a very important initial ingredient, because that sets up how the planets are going to be formed around it and what the planets are going to look like. In fact, we have a ton of theories that say that the compositions of stars should be somehow linked to the composition of the planets. And that brings me to the second step on this cosmic recipe for life, is that you need to form planets, right? You need to actually form these planets, and you need to form them with some certain elements, like the ones that we have at Earth. If by chance we had missed, I don't know, for some reason we had missed the delivery of water here on Earth, we wouldn't have the plentiful diversity of life that we see on Earth. So that was a very lucky alignment as well. So you need to form the planets with the right elements, and then therefore you need to understand how planets form. And the third one, which is super, super important, as we have seen it in the solar system, is that you need to develop a nice atmosphere. And if you notice, I like italicized nice atmosphere, because not any atmosphere will do. For instance, Venus and Mars, they're pretty similar in size and mass to the Earth, but they don't have nice atmospheres. Like, you wouldn't want to go on vacation on Mars and Venus. But Earth is kind of special in that sense. It has like the right amount of molecules to make it like warm and cozy. It has this, nitrogen base, but it also has a ton of oxygen that we can breathe, and we can exchange with plants with the carbon dioxide that we give out. So there's a mechanism, there's like an ecosystem that it's developed thanks to an atmosphere. So astronomically speaking, that's a very, very important end product. Like detecting atmosphere from other worlds, it's like a key concept that we need to develop and study in detail. So let me give you a small tour about what this has to do with Webb, because I've already given you an introduction to the 3 protagonists on our story, right? I gave you a small story about Webb at the beginning. I gave you a small introduction to why are we on the middle of this story, and I'm now giving you like a small brush on other worlds. So now let's put them all together. So what I'm gonna do is that I'm gonna give you a little tour on what this beautiful telescope is going to be doing on these 3 steps of this cosmic recipe for life. So let's start with the first step, right? At the beginning, with making a star. So the very nice thing about the James Webb Space Telescope is that this telescope, it's going to be able to look in colors that we are not able to look at. So the colors that you see, my shirt, my face, and the colors that you're seeing in this presentation right now, this beautiful, beautiful picture that you probably have seen before, these pillars of creation. All these pictures that I'm showing right now, there are in certain colors of light that our brain and our eyes can detect, which is called visual. We call it the visual colors, which are the ones that you and I can look at. Now, Webb will actually be looking at infrared light, and we humans cannot look in infrared light. And this is the amazing thing of being a human, I think, on that we can develop instruments that can look with eyes that we don't have. That's completely amazing, right? And we should be proud of that as well. And in particular, why a picture like this one is so important to look into the infrared, to look in as many colors as you can, is because these pillars of creation, this beautiful structure that you're seeing, this astronomical structure that you're seeing here, it's actually a stellar nursery. This is where stars are born. And the reason is that to form stars, you need other 2 ingredients, basically. You need gas, so you need elements that form the stars, our own sun is a big ball of gas. But you also need dust, which is this dark thing that you're seeing here. Dust is very important, because if you just bring gas to the ingredients, to your bowl while you're making, a star, if you only bring gas, the gas will go away. Because, as any gas, what you do, if you try to trap it, it will escape. And that's because it's hot. But bring dust to the question. Dust is typically, in astronomical scales, dust is very cold. and even if you pick dust outside, it's quite cold actually. So you need like copious amounts of dust and couple that with gas so the gas does not escape and it gets together and it shrinks and it forms stars. So you need both. You need dust and stars. What you're seeing here is dust, and with important, dust is very important, but the problem is that in visual colors, dust looks very dark. As you're seeing here, I cannot see beyond this dust. And that's complicated because it doesn't let us look into the very details on where the stars are actually forming, which are actually in these clumps of dust. And enter infrared light. And infrared light is amazing. Here's an example before showing you what you're gonna see in infrared in the pillars of creation. Here's a human in visual colors, a random human in visual colors. So in visual colors, the colors that you and I can see, we see, of course, the face of this human, glasses, mouth, and everything. But there's one arm, one arm at least, that it's hidden behind this, this trash bag on this. You cannot see it. But if you put your infrared glasses, you can see beyond that. You can see the, the invisible. So this is the beauty of observing with the glasses that Webb it has. That it allows you to see stuff that you otherwise couldn't. And the reason for this, the reason why are you doing this in the infrared and you can observe this human in the infrared is that we humans, we emit light. Like right now, the light that you're seeing from me, you're seeing reflected light right now because you only see the visual colors and everything in the visual colors around you is reflecting light. But if you could look in the infrared, you would see humans glowing. And again, the reason for that is that everything that has temperature emits light. And depending on your temperature, you emit different colors of light. In particular, us humans, we have such cold temperatures that we emit in the infrared. And this is exactly why we're able to see, in this invisible hand that before we couldn't see. It's because we humans glow in the infrared. And if you put infrared glasses, the bag is not radiating light, but the hand is. So we can see beyond. We can see, we can see through other stuff. So now take a look at the pillars of creation. Now you're seeing in the visual colors, and I'm going to swap, and I'm going to show you how it looks in the infrared. So look at that. So in the infrared, just by switching those glasses, you can see beyond. You can see behind what's happening in the dust and in the interior of what's happening in the dust. And this is going to enable us to extract a ton of details about what is actually going on when you form stars. We're going to be able to tell the composition of that gas that's starting, that the initial elements of what forms a star. We're going to be able actually to study dust properties. If I put my infrared colors in the farthest infrared, dust actually start glowing, in fact. So we will be able, and Webb has all these instruments. So Webb is going to be able to see all the way from studying the properties of dust itself to seeing behind the dust and tell us all the little details about how stars form. Okay, so that's step one, right? Making a star. What about step two? What is Webb going to tell us about how to form planets or moons even? So, when stars are formed, so, after we make step one, we make a star at the center, there's still some material that is going around. And they form what we call in astronomy a protoplanetary disk. And this is what I'm showing in this video here, which is the protoplanetary disk that as time goes by, planets start to form and they start to absorb. So that's why you see some rings. Planets start to eat up some of this material. And, this primordial material that formed the disk, that's like the initial seeds of what formed the planets that we see in the solar system now. The beauty of the whole of this whole telescope is that Webb is going to be able to resolve the composition of those planet-forming disks. We call them protoplanetary disks because they're before the planets. And this beauty, it's also allowed not only by being able to look in infrared light, but also because of the fact that the diameter of the telescope is so large, 6.5 meters. We haven't looked at the universe with such a large diameter telescope. This is going to enable us to see little details about these disks and even detect and characterize some of these newborn planets. We're going to be able to detect planets that are just forming, like baby planets. And the reason for that is that they are just forming and they're not that they're hot for astronomical scales, but they're just at the peak of what Webb we're going to be able to detect. And the most important part of all this is that Webb is going to be able to tell us the composition of everything that's going on in these disks. And here I think this is the only plot that I'm going to show. Oh, no, there's two plots. This one and another one that I'm going to show in a minute. Webb, it's able to decompose the light in the different colors. So in the x-axis that you're seeing here, the wavelength of light in microns, that's the color of light. And the more to the right you go, the larger the number, the more deeper in the infrared you're going. The y-axis here shows the brightness of light, how much light you have at different colors. And this is fantastic because different molecules like to emit light and also absorb light at different colors. So for instance, take a look here, there's like a zoom to a methane signature. And we know that only methane emits at that color of light. So if we see a peak like that in a protoplanetary disk, we know it has methane. We can do the same thing with ammonia here, acetylene, hydrogen cyanide, carbon dioxide. And these molecules are very important because these are the building blocks of what we know as life. And these are the building blocks of these planets that are going to be formed. And this is extremely important for us to understand how these planets actually get to be and actually get the compositions that we get to see like in a system like the solar system. So Webb is really going to delve into the little details about how these disks are formed and therefore how these planets are going to be in the future. We're going to be able to predict how these planets are going to grow. Like imagine how cool that is. And the final step really is like, okay, once you've had these disks and you form these planets with the different compositions, how these planets actually look like. And that puts us into the third part of this recipe, which is developing a nice atmosphere. And this actually brings us to the whole idea of what a nice atmosphere looks like for us humans. And in particular, you can take a hint from the solar system. Venus, for instance, is just too close to the sun, and that's why it's so hot. On top of that, it has an atmosphere that creates a greenhouse effect that just blows this up, and then you have scorching temperatures in the surface that you don't want to go on vacation to Venus. And then you have Mars that has like a very tiny atmosphere, like a very thin atmosphere. It's colder because it's farther away, so it's also not very suitable for life. But we on Earth, we have like the right composition, and we're at the right distance from the sun. This creates the concept of the habitable zone. I really don't like the word habitable zone because habitable to us, to you and me, means much more than just being at the right distance. But this is a starting point in that we are looking to study, whenever we want to search for, say, life, we're looking to study planets for which the radiation that we receive from their stars is similar to the radiation that we receive here on Earth. And we call those planets that are at those distances habitable zone planets. Again, the only thing that habitable zone means is that you're at the right distance. It doesn't mean that it's actually habitable. I mean, in theory, Mars and Venus are in some optimistic regions of that habitable zone, but they are not habitable for sure. And there might be worlds out there that have like the wrong composition for the atmosphere, at least for us humans. And even though they can be at the right distances, they might not have the right atmosphere for us to consider that habitable. So whenever you hear in the press like habitable zone, just take it with a grain of salt. Now, we've discovered planets that are in these habitable zones. And in particular, I always get asked, what is your favorite planet that is in the habitable zone? And I don't have a planet. I have a system that it's my favorite exoplanetary system. And my favorite exoplanetary system is the Trappist 1 system that you're seeing here. Well, this is of course an artistic impression of this system. This system, it's a system that it's very, very weird. It's very alien. It's alien all caps. Like it's extremely alien. It's a system that it's 40 light years away. That means that if you throw a ray of light in that direction, it will take 40 years to get there. So, light is very fast, 300,000 kilometers per second. So for light to take 40 years, it's very, very far away. But in astronomical scales, that's actually pretty close, like with my astronomer hat on. This system, it's a planetary system that has 7, like not 1, not 2 or 3, like we have in the solar system, but 7 planets that are more or less the size of the Earth. And they orbit, listen to this, they orbit a star that is very small. The size of the star that these planets orbit is the size of Jupiter. That's mind-blowing. It's completely, and again, it's very alien, it's very weird, but it exists, and that's the reality of this system. So in this actually was the cover of the magazine Nature, in which this article was published, uncovering the discovery of these 7 Earth-sized planets around the TRAPPIST-1 star. And I love this depiction because it shows the habitable zone very, very nicely. So the planets that are closer to the star, the ones in the interior orbits, they have like vapor going around. And the reason for that is that they're too close to the star, such that if they had liquid water in their surfaces, it will be so hot that it will be evaporated. So in the other side, the planets that are farther away, there's some ice you see in this table. And that's because these planets are so far away that if they had liquid water in the surface, then that water will be most likely frozen. But just a handful of planets, like 3 planets in the central part, there's water. The reason for that is that they're just at this right distance. And actually, that's the actual definition of the habitable zone. The actual definition is they're at a distance, assuming that they have an atmosphere like the Earth, such that if they're at this distance in this habitable zone, they could have liquid water in the surfaces. Like that's the exact definition of the habitable zone. But the reality of things is that we don't know much of the atmosphere. I'm gonna go that in a little bit. But I wanted to show you also something else that makes these worlds very, very alien. And also I brought like an artistic impression that I hope it's gonna blow your minds as it blew mine. This system, it's extremely packed. So here's a comparison of the size of the orbits of the planets as compared to the inner solar system. So in the bottom plot here. So you see Mercury, Venus, Earth, and Mars to scale. And the 7 Earth-sized planets in the TRAPPIST-1 system, they're all packed in an orbit much, much smaller than the orbit of Mercury. And they're all very close together. Very, very close together. Why I'm saying that I'm going to show you now an artistic impression that's going to blow your minds is that the thing is that these planets are so close with each other that if you could stand in one of these planets, and in particular, I'm going to bring you to, like, this is of course artistic impression, it's not a real thing. But if you could sit down on TRAPPIST-1 planet E, it has an E letter down to it. If you could stand on that planet, all the other planets will be so close that you would see them in the sky as we see the moon. So you would see other planets in the sky as big as we see our moon. Imagine that. You would be able to tell like a friend on planet D or F what's going to be the weather like the next day. And here's an artistic impression. This image credit goes to Geroditis, an artist that actually made this mock-up world in which, like, if you could sit down in TRAPPIST-1e, this could be one of the views that you could have. You could see the other planets. You see these other blobs in the sky. Those would be the other planets. Isn't that amazing? That's incredible. You will be able to see like clouds, like how cloudy these other worlds are. It's pretty impressive. Now the big question is, do these planets actually have atmospheres? Could we actually move there? Could we go with a spaceship and have this beautiful view that I just imagined with you folks in this previous artistic impression? And here's where Webb enters. So the huge advantage, and this is the first time that we will be able to do this, is that Webb has the power to detect the atmospheres of Earth-sized worlds. So we will be able, for the first time, to be able to detect atmospheres from these small Earth-sized planets. We couldn't before because our telescopes were too small. The colors of light that we were looking at were not the right ones to be able to make these detections. But now we have this beautiful telescope on sky that it's going to be able to actually perform these detections. It's going to be able to extract the information. It's going to be able to extract the light that we receive from these systems. And it's going to dismember it on the different colors of light. And again, the same thing that I spoke to you about the protoplanetary disks, we're going to be able to do it for these worlds. So here's the second plot. I promise that there are only 2 plots. This is the other one. And the x-axis, again, is the wavelength or the color of light. So again, the more to the right you go, the more to the infrared you delve into. And the y-axis is the amount of light that you received at each of these colors from a planet like Earth. This is like an Earth-like exoplanet spectrum. That's how we call this plot, spectrum. And as you see, yeah, molecular oxygen and ozone have features that are only at the very left end, like at the very bluish wavelengths, and the very bluish colors. But then in the infrared, it's very, very rich of elements. Like you can see, you can detect features of water, you can detect features of methane, carbon dioxide, even ozone, some features here. So we can make these fingerprints, we can take these fingerprints and analyze them here at Earth and be able to say, yes, this planet has an atmosphere, and even maybe detect, say, stuff like carbon dioxide from these planets. So this is, again, the first time humanity has been able to do these kind of measurements. And we're like one step closer then to figuring out life on other worlds. I don't think Webb would actually uncover life, but we will perform the first atmospheric detections. And that's going to be mind-blowing. That's going to be a huge step, like a huge leap forward to going down to understanding life fingerprints. So in summary, I gave you this recipe for life, and I've given you how Webb is going to explore this. So first of all, around Webb is going to be able to, explore stellar nurseries and tell us how to make a star. Webb is going to allow us to, understand how its planets are formed, what the composition of these protoplanetary disks that form these planets, the seeds for these planets look like. And it's also going to enable us for the first time in human history to unveil, to detect atmospheres of Earth-like worlds. So this is really an exciting time to be alive, an exciting time for me and for you to be enjoying the fruits of this telescope. And as I just told you, Webb will provide then key insights to understand how life emerges at the end, at least life how we know it. So again, 3 protagonists, of course, the telescope that is going to enable this window, these other worlds, but also us. I think that's also a very important path and a very important protagonist on this story, us, how we get, our minds transformed by what Webb is going to uncover from other worlds out there and how life emerges. That's it. I would like now to open it to questions, and thanks for your attention. Hope you enjoyed this tour to what Webb can do.
Great. Thank you. Thank you so much. I'll just tell you from my perspective, I'm very impressed with how little text you used in your slides. You have such great slides and such great graphics on them. And yeah, that artist rendition of a possible sky on Trappist, man, that was cool. And right. Grace said here in the comments that there'd be some great sky watching. And I suppose that's true for the most part, but of course, if all those planets were up at night, that'd be worse than having the full moon up at night if you're an astronomer on the ground. You don't like that so much. But anyway, I digress. Okay, let's see. I know we got a couple. There was a couple that came in earlier. So one of our questions, is life possible without liquid water?
Not as we know it, but we can be surprised. I mean, again, this is how we approach this question. Might not be the case in other worlds. And I do know there's biologists studying this. So as far as we know, all of them include water in one form or another. But what do we know?
Yeah, I think the general question or answer to that question for now anyway is no. But right, that could change. Who knows? Okay, another one is how sorry, here we go. How do you detect exoplanets? Is it indirectly? And how much detail can you see in exoplanets?
Right. Yeah. There's only four of the most important techniques. I'm just going to mention 2. The most popular technique, which we have uncovered most of these exoplanets, like several thousands of them, is the transit technique, and that's an indirect technique. So what happens is that we just stare at a star. It's an extremely boring thing to do, right? You stare at a star for like days and weeks and months until you see a little dip in the light that you receive from the star. And that happens because a planet passes in front of the star and blocks part of the light from the star. We call that a transit. But that happens periodically, then you typically claim that you possibly detected an exoplanet. And that's the most popular technique with which we've uncovered most of the planets so far. But there's other techniques that might seem to be a little more direct. For instance, there's a technique which is called direct imaging, which is actually a direct photo So the problem typically with doing that, like when you ask people in the first time, how do you imagine we detect exoplanets? Most of people say like, oh, you just go to a telescope and just look through it, and if you see a planet around, that's it. That would actually work in theory. The problem is that stars are too bright. So we have to use little instruments called coronagraphs that block the light from the star. Just as you in the night, you're waiting for a taxi or a bus, and then the lights don't let you see if it's a taxi or a bus or something else, and you have to block it with your own hands. We do the same thing for stars, but with a little needle. And that allows us to see the planets going around and take like pictures. Now, those pictures do not have resolution to see like the structure of the atmosphere. It's just like a little dot. But we can study that little dot at different wavelengths and different colors of light to be able to tell you like, yeah, it has methane, it has carbon dioxide, etc. That technique, however, only works for very giant planets and very young planets. But by the 2050s, we're planning to launch a mission perhaps to, for the first time, being able to image Earth-sized worlds like our own around other stars and take like pictures like those ones. But that's in the future. But those two are, the most representative for the question here. So most of them are very indirect. Yes.
Another question asking about, I think this is idea of terraforming. Is that possible on an exoplanet? Can you take carbon dioxide and convert that to pull the oxygen out?
Yeah, I think that's a very tough question to answer right now, because we don't even know if that's possible to do it on our solar system planets. So we know even less about exoplanets. We have been already surprised by the diversity of worlds out there. So I wouldn't envision a yes or a no right now, because we're just about to start exploring other worlds or the atmospheres of Earth-sized planets around other stars. And what do we know? Maybe our solar system planets are completely alien, and we start observing different compositions that don't make sense to a solar system. That could happen, but we are about to embark into that quest right now, so we don't know.
Well, at one time, the idea of like these hot Jupiters, lots of large planets like Jupiter is very close to their sun. That at one time seemed to be a norm, where it seemed to be like our solar system makeup was bizarre.
Yeah, exactly. In fact, for the hot Jupiters, these are Jupiter-sized planets that are in orbits like as small as a day. So imagine a year in those planets is like a day. That's what it takes to go around. That'll be pretty fun, like celebration every one day. Yay, New Year's. But right, when the first hot Jupiter was discovered, people didn't believe that was true. They thought it was some kind of error in the data or something like that. So it took a while. But yes, we've seen bizarre stuff. And that could very, very well be the case for the atmospheres of these Earth-sized worlds that we're about to uncover. Yeah.
Another question asking if Webb would be able to separate the Trappist planets from the sun and from each other. Will it have that kind of resolution?
Yeah, so how we're going to start is an excellent question. What we're going to do with the TRAPPIST-1 planets is that, so one of the properties that they have is that they transit. So that's the technique that we're going to use to characterize these exoplanets. It's not, we're not able to detect like a photo of them. We see them indirectly. And the technique that we used, it's a special technique called transmission spectroscopies. It's a very clever thing. So what we do is that we wait until the planets pass in front of the star. And then when the planet is blocking part of the light of the star, there's some starlight that goes through the atmosphere. And believe it or not, we have the techniques and the instruments on board Webb to actually extract those signatures from the light that we receive from the star. So all these methodologies are, of course, indirect. So we're not able to directly see the planets. But again, we can extract the details of their atmospheres if they are there. That's a very big question. Do they even have atmospheres? We don't know. We're going to explore it now.
Great. This is an interesting question. It's a good question. It's a common problem in astronomy. So they're basically wondering is how accurate will spectra analysis be from James Webb? Because you could have a situation where light from a planet or a star is passing through a cloud of gas between the telescope and that object it's observing. So how do you sort that out?
Yeah, no, it's true. It's a complicated process. Like we've been thinking on this for at least 2 decades right now. And it's a complicated process, but I think we understand it now very, very well. And we've tested it with other planets, like with giant planets. We discover atmospheres around them like every every other 2 weeks or so. There's a paper coming out with an atmosphere of a giant planet. So we have been well trained on uncovering these little signatures. But yes, it's a complex process. But again, we know how to do it as of today.
Excellent, excellent. Let me go through here before I go look on this other. Okay, here's a question from YouTube. Are the Trappist planets tidally locked? Will JWST be able to tell us anything about that?
Good question. Most likely not, because they're just too far away. But I wouldn't put my hands in the fire. In theory, there's ways in which we could tell with Webb if this was the case. But most likely, well, I wouldn't put my hands in the fire for the inner planets. But we will see. In theory, there's ways in which we could infer that from our observations of their atmospheres. Yes.
Another one related to Trappist. When might we start seeing data from those observations from other Trappist systems?
Excellent question. So the reality of things is that right now we're going through commissioning of Webb, and this commissioning phase ends on June, July. July is really the month that we're targeting. And after that, scientific observation starts. So we just liberate the observatory for everyone, for all the scientists to use. And actually the programs were just released 2 days ago, actually. So we know the schedule, what Webb's gonna be observing. And actually there's some observations in July itself for TRAPPIST-1, for some of the TRAPPIST-1 system planets. So we might have news on that, later this year, even like very nearby. It's like it's happening.
Awesome. And before we go on to the next one, maybe you could explain how is it determined what James Webb is going to observe?
Yeah, that's an excellent question. So yeah, who decides this? And it's like a mastermind thing, like this defining all this. Well, we astronomers have been organized, and in particular, a ton of this sorting of what is observed or not is done by the community itself. And it's organized here at Space Telescope. And the Space Telescope Science Institute runs these, we call them the time allocation committees. It's a committee that defines what's going to be observed. So how this works is that there's a call. This call was November 2020. There was the deadline. And then by that deadline, the astronomers and teams around the world will send proposals, written proposals. So this is like 5 to 10 to 15 pages explaining why Webb should observe my favorite object. After that, I was part of many teams and led a couple proposals as well. After that, those proposals enter the system, and then Space Telescope grabs them and tries to get astronomers to review them from the community. So they ask, like 100 of astronomers more or less, if they would like to be part of this committee, and they join. And then these folks are the ones that revise this proposal and they discuss them. It's like a week-long or 2 weeks long discussion on, yes, this proposal should make it. No, this proposal shouldn't because it has like this problem or not. This is the most exciting and so on. Then they're ranked. And once they're ranked, that's how it is defined. And at the end of the day, it's the director of the Space Telescope Science Institute, the one that signs, yes, this is the final, given this recommendation from the panel. So you see, it's a very sorted out process, and it goes every year in theory. So the next deadline for the cycle 2 call proposals is going to most likely be next year in January. That's the working date right now. It could change. So by the end of the year, we will all be working hard and trying to put new proposals and to see what Webb is going to observe in the next cycle.
Yes, writing proposals is just as much a part of science as making observations.
Yeah, that people don't sometimes they don't see or they don't see directly, but a ton of science is writing and convincing, and it's very, very interesting on its own.
Necessary evil. What are, I think in general, what are some of the most obvious biomarkers, and is there a definitive way to say that there is life on a planet?
That is a very complex question. because it's tough for us to make sense of what the chemistry in these other worlds actually is. And we understand the chemistry on the Earth mostly. We understand mostly the chemistry on Mars and Venus. To a certain degree, we still have many questions on there, even for the solar system. And now we want to understand the ones in other worlds, and that's going to get complicated. So if we see like the same ozone in an Earth-sized planet around another star as we see on Earth, is that a marker, or could it be that that planet has a slightly different composition to the Earth? It just creates more ozone out of its cycle. That's going to be one of the very big questions of humanity. Once we make the first detections of, say, we're able to measure that the composition of that planet is something similar to the Earth, saying that it has life or not is going to be a question that's going to take many years. It's not going to be an eureka moment. That's what I want to like for people to be aware of. Like the scientific discussion is going to be on and on for years. And we've already had a glimpse of this. I don't know if you folks saw, was it last year or 2 years ago, there was a detection of phosphine in Venus. And there were some people saying, phosphine, that's life. And then there was another set of astronomers saying like, I don't think that signal was real. So some people reanalyzed the data. Some other people looked at the chemistry and said like, there's ways of forming that phosphine in other ways, chemical pathways that are not standard. And that same discussion is going to happen in exoplanets. Like I can give that for written, and that's good. That's the skepticism, friendly skepticism that we have in science. So it's going to take us a while. And answering the question like, is there a special biomarker? The answer is no. The answer is that we will have to take each planet on a case-by-case basis. There's like not a common thing that you can say like, if it has this, it has life. As far as I understand it today, we're still trying to figure that one out.
Yeah, that observation of Venus was interesting. There's 3 missions, 2 US, 1 European, getting ready to launch to Venus over the next decade. So I'm sure that's going to come back up.
Oh yeah, definitely.
That will definitely come back up. What if life beyond Earth is somewhere hidden in dark matter / dark energy? How much time will it take for us to study dark matter in depth?
Yeah, I mean, there's ways in which I can think that this could happen, like especially with dark matter. So the big problem with dark matter is that we don't have no idea what it is. And we see its impact on gravitationally, but we don't know how it interacts with light. And as far as we understand it, that thing does not interact with light. So for us to extract some information from, stuff hidden in clumps of dark matter, if they exist, I don't think that would be the case. But even if they did, it would be very, very tough. Because I don't know the composition of dark matter, I cannot speak about what exactly it can do for life or hit for life. And the same goes for dark energy. Dark energy, we only see its impact on a cosmic scale. We see that the universe expands in an accelerated fashion, but we don't actually know what that dark energy actually is, like physically speaking. Like I can tell you, I don't know, electrical energy, I know how to explain it, like how it's formed, how it interacts, but I cannot tell you the same thing from dark energy. We only understand the macroscopic properties of them. So for me, it's very hard to link this question together with the concept of life because we don't know what they're made of, and therefore we don't know the impact that it has on life itself.
Right. Yep. Lots of unknowns. Will we be looking at transmission spectra of exoplanetary atmospheres, not only to determine their composition, but also to discover any combination of molecules and disequilibria that might hint at life processes?
Yeah, I mean, that's how it goes. So we of course have models of like what these Earth-sized atmospheres should look like around their stars. But yes, I mean, most of these models, we typically assume same conditions as Earth. But what this person might be referring in terms of disequilibrium is what I was referring before. Like, oh, if you have like extra ozone, could that be by some kind of internal process that the planet has, like a slightly different cycle to the carbon cycle that we have here on Earth, for instance? That could create like a different kind of atmosphere to the one that we're seeing. So yes, that's what we're trying to uncover. Try to extract the molecules, the signature of the molecules, and trying to make up the chemistry, try to understand the chemistry of that atmosphere. Yeah.
Do binary star systems, do they have planets?
That's a very good question. Yes, yeah, there's been some Tatooines discovered by some missions for the Star Wars fans out there. Yes, they exist. And so far, I can't remember if there's like one of these planets in the habitable zones, at least Earth-sized planets. I don't think they have been discovered. So the real Tatooine, probably not. Unless it's a moon, because there's giant planets close to the habitable zones of these two star systems, I think. But yes, the answer is yes, there's planets around these binary stars. Yeah.
Interesting. Kepler tests and huge telescopes from the ground have refined several of the parameters of the Drake equation. What does it look like now, and how can we expect JWST to refine them further?
Yeah, it's very tough. Actually, the only number that the telescopes that, like the missions that detect exoplanets, the only number that they have been able to constrain, and with huge error bars, is what we call eta Earth, which is basically the rate of planets around of planets like Earth around other stars like the sun. And that number is like between below 1%, and it can be all the way to 10. Like it has a huge error bar, even with all these missions that we've been having. But for the rest of the parameters of the Drake equation, we have mostly nothing. And just to remind everyone, I mean, one of these terms is, what's the amount of planets like Earth that host life? We don't know. From the solar system, that's 1 out of 3 in theory. But we don't know what that number is around other stars. Then the next number is like how many of those planets that are suitable for life actually have life. And of course, we know just one. And then even further, which ones of those develop technology? And that's by the way, that question of which planets develop technology, that question is a function of time. That's a variable that people typically don't think about, in that our technology for communicating with radioelectrical devices, with radio waves in particular, well, electromagnetic waves is the word I was looking for, it only developed in the past 100 years. It's very recent in the whole history of life. So we're talking about 4.5 billion years of life of the Earth, and only in the last 100 we've developed that. So we can detect maybe Webb will detect some atmospheres of these Earth-sized worlds, but that's a function of time. We will detect them at a certain time. What if we detect them too early and technology has not been able to develop, or life for that matter? So I think still the Drake equation is extremely uncertain. We have basically one term with huge error bars, and the rest ones are huge unknowns.
Yeah, it's still a fun little exercise to go through, though.
Yeah.
So we are at the top of the hour, so I want to thank everybody who has submitted questions, and Dr. Espinoza for taking the time to answer them. I just want to ask one more here, which I think is a nice one to end on. So of the 5,000 plus exoplanets that have been found to date, have you discovered any of them?
Yeah, I have the privilege of uncovering, participating at least on almost 100 of them, and leading, I think, in the order of tens. So yeah, I mean, it's been an exciting experience, but I would want to make something clear. It's not that I, Néstor Espinoza, went on my way and I uncovered planets. We work in teams. Science today is built on teams. So there's engineers, there's technicians, there's other scientists that do stuff that I don't know, that we gather around and join our forces to uncover these exoplanets, to make this happen, to make this enterprise of exoplanet discovery happen. You need teams. And that's a very important thing of science today. Science today does not work really like a lone wolf or like a lone genius. That really does not exist. The reality of things is that we work in teams, and I've been very privileged to be part of amazing teams of talented and diverse people that allows for this thing to happen, for us humans to be able to say that we've been uncovering new worlds out there. So yeah.
All right, very good. an excellent message to end there. Grace, we have a couple more polls, or are we holding off on that for a second?
Yeah, we have a couple more poll questions. Everyone, please give your thanks to an awesome presentation by Dr. Espinoza. Virtual claps. We really enjoyed it. Lots of folks on YouTube enjoyed it. So I've got a couple polls. Please stick around and answer them. And then after they're done, you're going to be rerouted to a survey, and we'd love your feedback. So I'm going to launch the polls now. There's 3 of them. You'll have to scroll. But we would just like to know how this program affected your interest and awareness in the JWST and its scientific mission. If you're likely to come back, we hope you do, for another one of our talks. The next one will be held on May 12th, and it will be the last one in our series. And we'll have a wrap up about the current state of the JWST and what to expect from its first year in space. And then finally, if you are interested in receiving any email notifications, you can respond and we can automatically sign you up for some of our newsletters. I'm going to give you guys a couple more seconds. All right, and 3, 2, and 1. Okay, thanks everybody for your participation.
Thank you all, and thank you again, Dr. Néstor Espinoza, Space Telescope Science Institute, and James Webb Space Telescope Extraordinaire. So thank you all for joining us again tonight, and we hope we'll see you again on May 12th for our final presentation in this series.
Bye-bye. Thank you, folks.